Fourier transform, part 2. So, we have seen previously that if at t, the input signal, and yt, the output signal of a LTI system with impulse response ht, then we would have this equation. Y omega is equal to h omega times x omega. So therefore, we can perform LTI system analysis with Fourier transform in a way similar to that of Laplace transform. But bear in mind, Fourier transform is more restrictive compared to Laplace transform. Why? Because the system for Fourier transform must be stable and the input signal, which is the xt, must be Fourier transformable. On the other hand, Laplace transform can be used to analyze stable and also unstable systems and apply to signals that grow exponentially. So if a system is stable, it can be shown that the frequency response of the system Hj omega is just the Fourier transform of Ht or H omega. So H omega is equal to Hs. The Fourier transform is equal to the Laplace transform provided that S is equal to J omega. For example, find the zero state response of a stable LTI system with the transfer function Hs is equal to 1 over s plus 2 and the input is given by exponent minus t ut. So, the Fourier transform of the input at t would be x omega is equal to 1 over j omega plus 1. So, you can get it from the table. So, since the system is stable, therefore, hj omega will be equal to h omega. Hence, you will have the equation to be 1 over j omega plus 2. Therefore, y omega is equal to h omega times s omega. So this will give you 1 over j omega plus 2 times j omega plus 1. So in the end, you will have yt is equal to exponent minus t. This is from j omega plus 1 minus exponent minus 2t. This is from j omega plus 2 times ut. Signal distortion during transmission. What is the characteristic of a system that allows signal to pass without any distortion? So a transmission is distortionless, meaning that no distortion, if only the output is identical to the input, meaning that it is the same, the output is the same as the input within a multiplicative constant and relative delay is allowed, where you have yt is equal to g naught at t minus td. So g naught here is the multiplicative constant and minus td here would be the relative delay. So this will give you y omega is equal to g naught x omega times exponent minus j omega t dt. So this is when you apply Fourier transform. But y omega over x omega is equal to h omega. Therefore, the frequency characteristic of a distortionless system is h omega is equal to g naught exponent minus j omega t dt. So we can separate those into two. So h omega is the g naught and the phase of the h omega would be the minus omega td. So this would be the magnitude and this one would be the phase. So the phase of H omega is equal to minus omega TD. Means that every spectral component is delayed by TD second. So there is a delay. Therefore, a distortionless transmission needs a flat amplitude response and a linear phase response. So Tg omega here is known as the group delay or the envelope delay. In Parsifal's theorem, the energy of a signal at t can be derived in time or frequency domain. So in time domain, you will have Ex is equal to the integration of the magnitude of xt squared dt. And in frequency domain, you will have it to be 1 over 2 pi, the integration of the magnitude of x omega squared d omega. Thus, the total energy would be the area under the curve of x omega squared versus omega, which is divided by 2 pi. So this would be the total energy, which is the area under the curve. If xt is a real signal, then x omega and x minus omega would be conjugate. Here you have the magnitude of x omega squared is equal to x omega times with the conjugate of x omega. So we already know that if you have the conjugate here, then we will have it in minus. So x omega times with x minus omega. So this implies that x omega is an even function. Therefore, your energy signal will be 1 over pi, the integration of the magnitude of x omega squared d omega. Consequently, the energy contributed by a real signal by spectral components between omega 1 and omega 2 would be 1 over pi, the integration from omega 1 to omega 2, x omega squared d omega. Next, let us look into filter. So what is a filter? A filter separates the wanted part of a signal from the useless part, meaning that you only want the wanted part of it. In the signal and system analysis, it is a device which separates the signal in one frequency range from the signal in another frequency range. So an ideal filter will pass all the signal power in its pass band. So the one that you wanted, the signals that you wanted will be in the pass band without any distortion and completely blocks the signal power outside its pass band. So filter has a transfer function, which is denoted by H omega, that allows or let through the frequency component of input signal within the passband. It also eliminates the frequency component of input signal within the stopband. Have a look at all these figures. So this is an example of an ideal low pass filter. So the passband would be this area over here, and the stopband would be these two areas at the right and left. So here it is allowing the low pass frequency, and then it is filtering out all the higher frequencies. Next, we have the ideal high pass filter. So the stop band would be at the low frequency here, and the pass band would be on the higher frequency. This is an ideal band pass filter. So this would be the stop band, So it is allowing the area from omega 1 to omega 2, and it is allowing the area from minus omega 1 to minus omega 2. So band stop filter would be the opposite of it. So this filter is stopping the frequency from omega 1 to omega 2 and also from minus omega 1 to minus omega 2.